Well, last time we had a little bit of a review. We showed how to kind of mathematically obtain the derivative of a sine function, and looked at the trivial problem of using the product rule to differentiate the formula for a straight line, where the slope is a constant term. Now we want to kind of move on and look at the rule for differentiating exponential functions. And I think you may have seen this rule, or you may have seen this relationship, which is really an incredible relationship, actually. But the derivative of e to the x is equal to e to the x, and we can just differentiate this thing over and over and over again, and it's always e to the x. But life becomes a little bit more complicated when this exponential function has a constant up here. It could be even just a minus sign, and that changes everything around. If this was a e to the x, we'd still get a e to the x, a e to the x, whatever. But if we put c up here, it's that this relationship doesn't work. However, the differentiation of the exponential function that we just looked at there, a times e to the cx, does fall out pretty simply. It's a two-term combination. The first term is just, okay, this is your function, rewrite it. Kind of comes from here. You might think of it as, okay, well, we do get that function back, but we do have to multiply it by the derivative of the exponent. So when we do that, we get, here's our original function, a e to the cx times the derivative of the exponent is just going to be c. So we get c a e to the cx. So this is really just an application of the basic rule for differentiating exponential functions, and it does incorporate a chain rule concept, where we think of e as e to some function h of x, and then we rewrite the derivative, and of course it could have a constant in front of it, so like it does up here, e to the h of x, whatever h of x is, and then we differentiate h, whatever it is, with respect to x, and multiply the two together. So that's a basic rule for exponential differentiation, and it works out pretty simply. You just have to remember there are two factors in the derivative. There's the original exponential function times the derivative of the exponent. Just a two-step process. If we did something like take the second derivative, that would just be, remember this is the first derivative, so that would just be the derivative of the first derivative. That would be the second derivative. So we'd be taking the derivative of c times a e to the cx dx. And again, it would be a two-step process. We would rewrite this original function, multiply it times the derivative of the exponent to give us c squared a e to the cx. Fairly straightforward, I hope. These rules are specific to the base e. So if you have a function which incorporates another base, like this relationship here, which is a relationship between the number of earthquakes of magnitude m and higher, m and greater, we have a base 10 relationship in here. And what we have to do in order to differentiate a function with an arbitrary base is we have to convert that base to a function of base e. So all we have to do is, in the case of base 10, is simply express 10 as e to the 2.3026 power. That's what 10 is in a base E representation. And 2.3026 would just be the natural log, or the ln of 10. So we're going to go through all the steps here, but so for a function like n is equal to k times 10 to the minus bm, n becomes n equal, just substituting in for e to the 2.3026 for 10, we get n is equal to k times e to the 2.3026 power raised to the minus bm power. So we know for our rules for handling exponents that we just multiply these two together. So that gives us n is equal to k e to the minus 2.3026 times b times m. Okay? Now, dn dm then is we've expressed n as in a base E formulation. So now we're just going to apply the rule that we already know. We rewrite the function ke to the minus 2.3026 times b times m, and then we take the derivative of the exponent with respect to m in this case. The derivative of the exponent with respect to m is just minus 2.3026 times b. B is a constant. Okay, so since e to the 2.3026 is equal to 10, just come back and look at this, we have e to the 2.3026 in here, we have 2.3026 in here. And e to the 2.3026 is n, and 2.3026 is the natural log of 10. We can rewrite that derivative. So we've written it out here. We just repeated what we showed on the previous slide. And this term up here in the exponent, e to the 2.3026 is going to be 10, so we can just change that back to 10 again. And then the minus 2.3026 is the natural log of 10, so we can change this to natural log of 10. And we see that what we end up with is, for our result, is that the derivative of n with respect to m is just minus b times the natural log of 10 times k times 10 to the minus bm power. So the only thing that's changed here from the rule that we use for differentiating an expression, an exponential function where the base is e, is that we've added this natural log of 10. Otherwise, everything else is the same. We have our original function here, k times 10 to the minus bm, and we have the derivative of the exponent, which is minus b. So we have minus b times k times 10 to the minus bm power, but we add this additional factor in here, natural log of 10. Now if you do use Wolfram Alpha, and a lot of students do, it's a good way to check things, it's a good way to learn, they go through the steps for you, so wouldn't discourage you from doing it, but when you do something like take the derivative of 10 to the ax, you'll get a result that looks like this, which is very similar to what we got, except that we have the log of 10, and in most cases we think of log, when it's spelled out like that, as being base 10. But this is natural log in this case. So look at the notes when you're using Wolfram Alpha. The log of x in this case is the natural log. It should be written ln of x. Okay, so in general, for y, if you have a function which is y equal to k times b, an arbitrary base, raised to the minus bx power, where b is this arbitrary base, we have to express b as equal to e to the n, right? So we have k e to the n raised to the minus bx power, or y is equal to k e to the minus nbx. So all we've done is we've just rewritten b as e to the n, substituted that back in. When we take the derivative, we use the rule that we developed earlier. This is just going to be the original function. We just rewrite this function, and then we multiply it by the derivative of the exponent, which is minus n times b. Okay? But n is the natural log of b, and e to the n is the base b. So again, I think you can see how we get the derivative here, which is equal to minus. The only thing which is different is this additional factor in here, the log of the base, whatever that happens to be. That gives us the result that we're looking for. So just add that factor in when the base is not equal to e. Okay, just a quick point here, and we'll have to come back to this later on, but the derivative of the log of x is equal to 1 over x, and that's something you should probably remember. We'll illustrate this graphically in, I think, the next slide set. But it's also has a chain rule component. So if we have y is equal to the natural log of f of x, dy dx is equal to, well, we take 1 over f of x, this kind of general rule applies, but then we multiply it by the derivative of the argument here, or the derivative of f of x with respect to x. So this again is a chain rule application, and depending on the nature of f of x, you'll probably find yourself using additional differentiation rules, a lot of which we've already covered. So let's see. The next time around, we're going to talk about some geophysical derivatives of some geological relationships, and so we'll actually be talking about a little bit of geology. So until then,